All right, can you see this now, sir?
Yes.
All right, awesome, awesome. So this is just a quick recap. We're starting with the Earth is flat. We're going to try and falsify that with some calculations and measurements based off of timing. And the null hypothesis is that the Earth is not flat. So if we falsify this, then this becomes true, right? Or you could, if you don't, or you could flip these either way. It doesn't matter how you want to look. Some people have a preference for them. But anyway, the example here we're going to be using is Pikes Peak. So this is the observer center here. This is the website that we use to calculate the distance, and that's going to be necessary for how we're going to do our triangle here to establish the angle. So you enter your coordinate. Well, I'll pull up the website here so you can go over it together. So what you would do is you would pull up this website here. You would enter your coordinates for your house or I'm sorry, wherever you're making your observation. So you can use GPS to get your coordinates. In this case, it's Mike's house. These aren't the coordinates to it, but anyway, and then you would enter the peak here that you're going to be observing. So you would just go to like Wikipedia or whatever. You can get the Pikes Peak information off of there, the lat long. You enter that. This is going to give you a distance to it and your final bearing. So the two important points that you're going to need here is your distance. This is going to be part of our triangle, and the final bearing is going to be useful for how we use stellarium later to look for stars that are going to be intersecting with our triangle.
Okay.
All right, and then we move on down here. So now we take the difference in elevation between this mountain peak and our observer point at our distance away, which comes out to be 50.7 kilometers away in this case. And that's going to give us an angle of 2 degrees and 31 arc minutes. So just the raw planar trigonometry of the difference in elevation, or the difference in altitude, and the distance here, it gives us the angle 231. And then when you do the arc sine of the radius and the distance, you get 2 degrees and 4 arc minutes for the globe prediction. So that's removing. Second thing for you, so we can do that. So it removes that. It comes out to 203. Actually, it's 204 with this is rounded down or whatever. But anyway, the globe predicts this angle due to the mountain being tilted away from you. It's going to be about 200 meters shy of what the flat Earth prediction is, and that makes it come out to 219 with refraction, essentially, right? So the way that we calculated it, doing the arc sine, we added celestial refraction to get us back up to what the globe predicts, so to speak. And then if you do it using 2 pi and then terrestrial refraction, adding 2 arc minutes, you get you get the same value here. So it's just 2 different ways to get the same thing. That'll be important later when you discuss this with other people, so that you know how we did it. So do you have any questions so far?
No, I guess not. I mean, I'm a little bit lost as to why you're saying that that's the globe prediction with the bend, but it's still going to take a tangent, right? We're still measuring from the tangent.
Yeah, it's just the deviation. You could do this using the 2 pi method that Ruhif likes to use, and then you would just it comes out to be 217. And you add 2 arc minutes for terrestrial refraction, and it comes out to 219. So either way you slice it, this mountain physically has to be 200 meters shorter than the flat Earth prediction. Essentially, that's all it comes. That's the big takeaway here, is that we have 2 different values for the altitude of the peak relative to us. And then now what we're going to do is we're going to take this.
Well, so stellarium though is going to show you where the star is compared to where the mountain is on the globe Earth, right?
So yeah, what we're going to do is we're going to go to the top of this mountain and we're going to use this angle, right? We didn't tell stellarium like how far away we were for our observer point. We're just going to line these up and see what happens, what we can do referencing that. And yeah, so stellarium would be using the graticule, the latitude longitude system, right? So that's the position of the stars as a snapshot on the vernal equinox. So that's what it's in reference to, the nautical almanac, essentially. So when you go into stellarium and you turn refraction off, it references the quote unquote true position of the star, which is just the nautical almanac position, which is where it's expected, or where it's expected to be. But then when they went and took measurements and it was never in the center of their theodolite. So that's where they came up with globe or whatever. But yeah, it's using that coordinate system for the positions of the stars at the time of this peak when we go into stellarium here. So all we did so far is just estimate what the angle would be based on our distance away from this mountain, based off of plane trig, and then based off of like globe slant, essentially. So we're just doing the arc sine of that. So now we have 2 elevations, and then now we go into stellarium here. Oops. Okay, so what we would do now is we would go into stellarium. We enter the coordinates for the mountain peak now. Bigger for you. So we enter the coordinates for the mountain peak, the lat long, and then we set our reticle up here to 2 degrees, 31 arc minutes, and we look for a star that's going to intersect at that time. Now, that final bearing that we got earlier when we did the calculation, so when a person is doing this themselves on that website, there's an order. So you enter your observation first, or your location first, and then you enter the peak that you're going to be looking at. And the final bearing gives you the direction that you'll be facing as if you were standing on the ground at your observation point, looking at that mountain peak. So this tells us where to turn, on a 360
Okay.
degree. So this tells us where to look, and then the elevation angle is our angle that we calculated, and then we turn refraction off down here at the bottom. When you mouse over, you can turn off refraction. So instead of seeing the apparent position, which at this location would be 2 degrees and 46 arc minutes, with refraction off, it's 231 or 232 for the true position right at this location. So now, and then we have this time that it's going to be at this location too, right? Because we played out the night sky, and then it's
But you're turning
paused.
off refraction just to check what its true position is.
Yes, just to check the true position because we're not concerned with where the star is when we like the visual position of it. We're going to be looking at when we can't see it anymore because we can see it, in the sky as it's coming down to the mountain, but we're concerned with it with the time that we can't see it. And the time that we expect not to see it will be when it's at this angle that corresponds to the same elevation of that mountain based on our calculation from our distance.
Okay.
So the time that we get is 6 p.m., 31 past the hour, 22 seconds on what was that, January 30th, 2025. So now we would, so let's say we did this before this date. So now we know where to look and what time. So now this date rolls around, and then we go and get our equipment out, not a Theodolite. We get our recording device so we can take video here. And then we see this star on the right here coming down to the mountain peak. Now we're taking we're taking video time lapse that's synced to our phone, which is synced to GPS time. So we're all on the same time.
Okay.
And then when the star isn't here, we note the time that it isn't there, right? And then if you plus or minus that 1 or 2 seconds, doesn't matter. You could 1 arc minute translates to 4 seconds in our time, right? So if we're off by 4 seconds or whatever, uh, the timing there, like the idea here is that the difference is going to be distinguishable enough from a flat Earth versus a globe, because if the timing based off of this angle, right, is going to be at 231, and then the globe Earth prediction being 219, right, it's going to be about 15 arc seconds less. So, or arc minutes less. Go ahead. So it's going to
So,
correspond to a longer time. Go ahead.
So my question is, if you're looking at the flat Earth results, but you're taking what's from Stellarium, then wouldn't you have to add the distance back into the mountain? Or where are you getting the flat Earth results from? You're just using just straight the height of the mountain and the distance that you're from it and saying everything else is planar?
Yeah. So, well, all we're doing so far is we're just seeing what the relative angle would be based on our distance using plane trig and figuring out how much it would be how much would be missing if there's a globe. And then we're on
Yeah, but what I'm
Stellarium.
saying is, so on
Yeah, go ahead.
Stellarium, though, it's going to take whatever is what it built into its numbers, right? So it's basically taking the curvature of the Earth into account when it gives you those answers, when it gives you the places that you should be looking for the star, right? Or where it should be crossing at that time.
Like a 69 mile per degree relationship.
Well, sure, but I mean,
'Cause
whatever angle it's telling you on Stellarium is from globe math, correct?
well, that's what has been asserted, right? That's what's
Right.
kind of
Okay.
that's what's in contention here. So we're going to
Okay.
reference this, and because the thing is if the Earth is a globe, then the star will never be occluded at the time that corresponds to the angle of 231. That's the big distinction here, because this is going to be it's going to be blocked by a physical obstruction. So refraction here isn't going to be an issue because we're only concerned with when we can't see it anymore. When we can't see it anymore, it's no longer being refracted, and that's going to correspond to a specific time based on
Right. I'm just
based
confused
on
by
our
that though.
angle. Yeah, go ahead.
So when the sun is supposedly set already,
Mhm.
but it's not set, isn't it the same thing that it'd be the equivalent of saying that it's not being refracted anymore because it's now below the horizon? But it is still refracted, right?
So if you can still visibly see the sun, either point could be in contention. I mean, like either position would be true, right? You could either say we're still seeing the physical or apparent sun,
Well, what I mean
and
is it's still being so it still has the light bending to your eye.
right. But
Okay.
but then like let's say like the sun will eventually set. Like it'll eventually not be visible for either of us, right? Like due to either Earth curvature or optical reasons. At
Okay.
some point when it's not visible, that's the exact time that we care about. Because at any time before that, it could be refracted up, et cetera, and that's not going to tell us anything, right?
Okay.
So if we had something that was big enough to block the sun per se, we could reference that raw elevation angle relative to where we calculate it from and distinguish, the two different predictions based off of how long it's going to take for that sun to be occluded. But so in the same respect, we're just doing that with a star because There's more of them, and it's easier
Okay.
or smaller. Um, so yeah, so it's going to correspond to a specific time based on the physical geometry of this place, right? Because Stellarium doesn't know where we're observing this from. It doesn't know that it would have to move the star to a different location to match the quote unquote
Yeah, I
globe.
don't think it does that.
Yeah. What's that?
I said, I don't think it does that. Okay, got you.
Yeah. So we've only referenced the mountain peak in here. So if it gets occluded by at the time that corresponds to this angle, that means that this elevation is physically 231. Now, a big point of contention here is that if you measure this mountain peak during the day with a theodolite, it's going to read about 219 plus or minus 1 arc minute.
Okay.
So we're saying our position is that this is a geometric measurement of the Euclidean spatial field where things actually reside in three-dimensional space. That's where, one second, I'm gonna get some water here.
Right, which would be different than where we see them, though.
100%. The visual field and the spatial field are different. Now, the globe or mainstream rather teaches us that the visual field is Euclidean as well, and most drawing perspectives and all that are based off of what do they call it? The 2-point rule, which is basically establishing
Have
you know,
levels.
yeah, with Euclidean geometry, essentially. So this is how it's taught to people, but we actually see, in curved visual space, which gets into a whole separate thing. But the important thing here is that we're saying that the visual field, when you optically measure this with a theodolite, you're going to get you're going to get that measurement of 219, and it's not going to be due to the mountain being, physically lower in elevation with respect to you. And we're testing that by seeing what time this star gets occluded. Because if it gets occluded at 2:22 p.m., then that corresponds to this angle at this specific time, which geometrically would work out like this right here. Even though we're not actually measuring this angle with a theodolite, the timing in which we no longer see this star only corresponds to this angle right here to be physically blocked at that time, as per the reference in Stellarium when these two would line up. Because that's all we've referenced. Go
So
ahead.
what I'm confused on is that then seems the same to me as the globe, because the globe is taking the tangent, which is essentially the exact same thing as the picture on the left. You drew the ground curving away, but that's not involved in the measurement at all.
Well, the globe actually predicts two different scenarios here.
Okay.
Like one for the physical timing, it would predict a different time, and then for the visual reference on the star, if you go here because we started to get the 219 to get here, we had to add refraction. So when you go here, you have to add refraction into your reference on here, which is going to put the star above this to not be occluded anyway. That's what I was saying earlier when I said that Stellarium doesn't know where we started from, like for distance wise away from the mountain.
Right.
All it knows is that this angle right here, and
But you don't
if
think it would change the further you went away from it, the closer you got to it, none of that would make a difference?
it would be relative to the calculation of the distance that you're at for that time.
Okay, so you've already factored that in. Got you.
Yeah. So this is a snapshot in time at a specific distance, and
I got you.
anyone that's 57 kilometers away along this would be occluded at that angle. So
Right.
if you were to be like 30 kilometers, this angle would change, which would change the timing, but it would now be relative to this new angle at that new distance. But
Okay.
it's always going to be the timing that corresponds to the planar trig, because
From the peak. Okay.
that's all that's been measured so far. So the way that this started out was some people were saying that this was backwards derived from the globe, and this is just like a one trick pony show or whatever kind of thing, and it only works with this specific peak at this distance and stuff. And then Mike started doing it with other peaks and other stars at different distances, and we have a whole spreadsheet of all that, of all these different stars that so far I went and verified all of these angles in Stellarium and the timings that he says that they got included, and they all match with that the plain trig for the flat Earth prediction. None of them correspond to the timing on the globe. Now, the last couple of times I argued this with the main globers that were trying to argue against it, or the main proponents of people that were trying to argue against it. They were
Yeah.
they were basically saying that this data was invalid or whatever, but it was all the measurements that were taken after the 9th were subject to what's it called, daylight savings time or whatever. So we changed an hour back, and then everything was fine. So there was just like a clerical error or whatever. So this doesn't. So this works at different distances, different mountain elevations, different angles, different stars. And then here's a quick. Yeah, go ahead.
What I'm confused about it still is that it seems to me that the star is taking its height above the ground, right, or is above the tangent, not above the actual physical place on the Earth, because your horizon is the tangent. So it's not going to be measuring from somewhere else when it tells you the star is so many degrees up. So I'm just wondering, you're basically taking a tangent and then saying we live on the tangent, and then saying it matches. So it's like, well, yeah, because you're taking it from the tangent, the flat level line that goes from my feet out, you're taking angles from there. That's what stellarium is showing you. It has to do that because it's taking your tangent. So if you move then to somewhere else, now you go to where the mountain is, let's say, then it's going to be telling you new numbers from there, right?
Yes. The point of it though is that stellarium doesn't know we're here.
Right, but
So
stellarium
so
knows the.
so
Okay,
so
go
ho-
ahead.
so hold on. So
Okay.
if you were to put this into stellarium here, like the globulars were doing uh beforehand, because they were saying like, you can't use this reference or whatever because your observation was here, but I'm saying our position is that the crosshair of our theodolite, so to speak, is this mountain, right? Our eyepiece is over here, so our theodolite is 50.7 kilometers long, and this would only be occluded by a mountain peak of an elevation of what was it, 2,270 or something like that, from the plane trig, because based off of this timing, that's the only way that this works out. So if you go into stellarium and put the observer here, you're going to predict that the star is way lower uh, down here, and it's not even going to be able to refract over the mountain to even do any of this.
Yeah, because it takes the tangent as the bottom. So you'd have to adjust everything because the tangent is the baseline, which is flat, which is level.
Yes.
So wouldn't you be the degrees that the star is above wherever you're taking that observation from? That's where it's getting that angle from. So, for instance, where this guy would lose the star on his horizon is from his tangent, and then where the other person would lose the star from the top of the mountain is going to be their tangent.
Well, they lose the star at the exact same time, so to speak, because if you're standing here, it's going to like the nautical almanac position, the true position is going to line up at that specific time. But the purpose here is that this isn't a tangent, right? This is a planar elevation angle based off of your distance to this object that has a physical elevation. And if you're on a globe, that elevation is going to be lower. That corresponds to a different time. So the big significant takeaway
The
here,
stellarium is from the globe.
I understand like what you're
Okay,
saying, and
gotcha.
if that were true, right, then this timing it would be measured later in the evening by like 14 to 18 seconds depending on the angle in the mountain. Like that's the significant part here, because this would be like an amazing globe proof if the timings actually matched due to globe slant to put that physical elevation peak there. That's the whole point of this, because this elevation peak can't be just on like some relative tangent and also occlude the star as it also intersects at that same angle here. That would be geometrically, that wouldn't line up. That wouldn't physically obstruct the star. It would still be visible, and then it would have to get lower in the horizon to get lower to that mountain peak that's missing about 200 meters from it.
So then, when you say you're taking the same number from the top of that peak, so explain to me what you meant by the star doesn't disappear for that person.
Well, there's only one person
Okay.
referencing this. We're using the peak of the mountain to occlude the star. All we did was go to stellarium at the peak of here, and then use the same angle that we calculated, that relative elevation angle based on our distance, and
Okay.
we just were like, hey, let's see if there's a star that when it intersects with this exact angle, if we also can't see it anymore, because that would
Okay.
mean that now it's being physically blocked by this at a specific time to cause that blockage.
So then, stellarium is wrong in your mind.
No.
Okay.
The way that we're using it is completely fine. This shows that the elevation angles of stars are actually with respect to planar geometry, right? Because all we did was
Right.
reference the so-called true position, and it matches a time that corresponds to a physical obstruction at a specific elevation angle that's different from what the globe picked.
I'll have to keep thinking about it because to me it just seems like that is what you would expect. I would expect the results to match a flat Earth if you're taking the tangent as the baseline, because
Yeah.
that's what it's getting. It has to get the height of the star from the tangent. It's not because even you said it doesn't know where you're at really. So it's the height of the star is above. Let's say from the tangent of where that mountain is. That's where it's getting the height of the star, right? Because it doesn't know where you're at. You're saying.
Yeah.
Okay.
Yeah. But the thing is though, is that like if this mountain were lower, right, it couldn't be occluded at that specific time, which was
Well, it would if you were
6
taking
p.m.
the height of the star off of the actual place it is on the Earth, because the Earth would have dropped, so the star would drop, right? Causing it to. I'm saying that it seems to me like we're getting the numbers from the globe, number one. And now number two is that it is a flat baseline. So you're using a tangent. So I guess I just don't understand where the curved Earth would come into it. You're saying that if it curved, then you're going to bring the mountain down, but
Yes.
it's
If
getting its position from the mountain on a globe, right?
but stellarium doesn't know any of that, bro.
Okay.
Like
So the stellarium is coming from the globe. Okay.
all that we all that is when you say the globe, like you know that you're just referencing a snapshot of the time of the sky, right? On the vernal
Okay.
equinox. So like all we're referencing when you say the globe, would be like that snapshot of the sky. And that's what defines the latitude and longitude systems. And everything is built on deviations from those points.
Correct. But
So
then your location on Earth, where it's saying that you might have a certain star occluded or whatever, is going to come from the tangent at that position.
it's going to come from,
Because you said it's not taking anything globe into account, then it's just getting
if,
the whatever
if it's, if it's,
observations.
listen, if it's based off of an elevation, right? Because the elevation of this mountain to us, right?
Okay.
It's either in physical reality, it's either going to be 2 degrees and 31 arc minutes relative to our position, or it's going to be 2 degrees and 19 arc minutes relative to our position. If we live on a flat Earth, then that's what this mountain peak is going to be. And if that's what this mountain peak is, then if there's a star in the sky that matches up at this angle at the time that we see that, or at the time that we don't see it anymore, then that means that the distance between us and the mountain is planar. The distance between us and the star, if you were to traverse it out to get under its GP, would also be planar. That's the implication of this because of that timing.
Right,
So,
but that's where the numbers come from, is the tangent, right? So that is planar. That's the bottom of the angle is flat line.
and if it were a globe, though, right,
You're still taking
this
the tangent.
and the timing would be different, though. Like, do you understand?
No, I
that
guess
if-
that's what I don't understand. So I don't understand why
Yeah.
the timing would be different, because it's
Yeah.
taking your known observation from the tangent. So then you guys are going out there and saying, okay, now we're taking the known observation from the tangent, and then it matches a flat Earth. But that's what you would expect. To me, I don't understand why you would expect something different.
What you-
Because go ahead.
I was gonna say, well, what you would expect is that the timing. Where's my? Oh,
Can you take me through? Maybe I'm not understanding the order of things correctly. Can you go back to the drawing and tell me what you did first?
Yeah.
Okay.
So what we started with was we're looking at a mountain peak, and we know how far we are with it, or how
Yeah.
far away we are from it, because
Right.
we used our latitude and longitude, and we went
Mhm.
to that website and we entered the latitude and longitude of the peak of the mountain, and it gave us the distance and the final bearing. Okay, and then we went into Stellarium and we took the angle that we got out of that calculation from our distance and or difference in altitude based off of our observation altitude and the peak of the mountain. Okay, so that gives us a raw 2 degrees 31 arc minutes for this elevation peak. So
Okay.
in other words, it's just the regular plane trig angle. And then you can take off 27 arc minutes from this for globe slant, which puts you down to 219 for the physical elevation relative to you at that distance. So because the Earth is a globe, this mountain peak has to be lower than the plane trig one, right? So that's all we've done so far is we just did 2 calculations to see what this relative angle would be.
Yeah, I guess I'm just confused as how that's not already taking the curve into account when you're going with the other one first. So if you're taking that angle to the star on the left side of the page over there
Mhm.
on the flat baseline, okay, great, I understand that. Then you're saying now we're going to say, well, what if we're on a globe and it has to lower? Well, but Stellarium is already taking that into account, right? Stellarium already took whether or not you're on a globe into account because it's based on the globe,
When we go to Stellarium on this mountain peak and we look up at 232 and
right?
we turn refraction on, star goes to 246,
Right.
right?
Okay.
So
And refraction was off. Why?
because we were referencing the true geometric position of the star.
Okay.
Just
So why
to-
would you do the same thing when you got to the mountain peak?
Because the mountain peak is occluding it. The mountain peak is the thing that's hiding the star from us that allows us to determine when we can't see it anymore to see if it was physically obstructed by it. It's part of our theodolite.
Right. I guess I got confused where you
So-
said, well, why did we turn off refraction?
Yes. To reference the true geometric position of the star to see if when that intersects with this mountain peak, if we can no longer see it. And if those line up, then it shows that the true position of the stars and and more importantly, the true elevation of this mountain peak to occlude said star, has a specific elevation to it. It's either going to be higher or lower based on the timing that we can no longer see the star.
Okay. That's the one part I don't get yet. You'll have to forgive me. I don't understand why you would turn off refraction in one instance but not the other. Because
Well-
to me, you're observing things through atmospheric conditions, and if there's a standard refraction that has been measured in some way, then it should be included.
Even without refraction, the timing still matches the flat Earth prediction.
Okay.
So it would like even if we left refraction off, right? We put it on because that's what the globularist would have us do, and if we don't put refraction on, they get really upset with us.
Of course.
But to even get us to 219, we had to do terrestrial refraction or celestial in the way that we calculated it, which gives us the same thing. And then when you would,
But you did that. Hold on. So you added refraction there, but you're saying you're not going to turn it on when it's on Stellarium.
No,
So just like
no, we did.
oh,
When you're on the peak, the 246 would be the visual representation of where it's like supposed to be or whatever, right?
okay.
And then we're saying that when its quote unquote true position intersects with this angle 231, that we can no longer see it, irrespective of any refraction or who's on top of the mountain. And the only way that could happen is if this mountain was actually at 231 and not 219, based on the time.
So you don't think refraction moves the star at all?
Well, it does, but when we can no longer see it, it's no longer being refracted, right?
No, I don't really understand that. Wherever we see it, it is being refracted at the place we see it.
Right. And then
Or
when
no.
we no longer see it, it's blocked by something because it's physically being obstructed. It's no longer there.
Sure, its apparent position is blocked by something. Yes.
Right. And when we no longer see it, that time is going to correspond to a specific angle. And that angle, if the Earth were a globe, is 219. So the time it would be like,
How many seconds
14,
are we talking?
so 11 seconds for like 40 seconds, 44 seconds.
Okay. Go ahead.
Yeah. So it would be, I mean, that's a huge, huge difference. And the only thing that's been measured is the ones that correspond to the flat Earth prediction.
Yeah, no, I think that I have to look at it obviously longer and figure it out because I'm kind of confused on the part about the tangent and where the star is being measured from each location. Because I would think that if you're talking about where a star is going to be blocked by a certain mountain, I don't really get how it wouldn't be dependent on where you're at. So that seems funny to me that you're saying that it doesn't know where we're at. You're just taking a distance away from it
Right.
and pretending that you're placing yourself where nobody is.
No,
And
we're
putting
not.
the
We're not
server-
placing anyone where anyone isn't. Using a mountain to block it, and if we can't see it at that time from where we're actually at, then that means, that object is physically there to block. That's all it means.
Yeah, but I'm saying you're taking the position of that mountain. So what happens if you go to Stellarium and just put in that position from that mountain? What does it say?
If it's going to say at that time, it's going to say 231 for the true position, and then when you turn refraction on, it'll be 246.
Got you. But when we're back behind, you're saying the globe prediction is whatever you said, 19, whatever, or 9.
Yeah, yeah. If you go to his house and do it, it'll be like 204. It puts it like hella below it. It's not even close.
Got you. Okay, that's it.
Yeah, that's basically it. And then so he reproduced this at different places, and I just wanted to show you a video of it real quick because it's super
Yeah,
cool.
please.
I think you would appreciate it either way. Change the. So here is the moon, and then there's a star under the moon, and as they're going down, they're going to get blocked by this mountain here.
It's a map of the Earth right there.
Yeah. Yep. So that's the primary premise of
Okay.
of how this is measured and done, and then we're just referencing the time that it got occluded. That's it.
Okay. But the position of the star in the sky, where is that being taken from?
From the Nautical Almanac, which is Stellarium, or that's what Stellarium uses.
Right.
It's just Nautical Almanac.
Which is taking, I guess, so that's what I'm trying to figure out. So if you're talking about a location where you're observing it from, and then you're getting a height above the ground, that's a height above the tangent, right?
Yeah, all we're doing is referencing the relative angle of the whatever peak that would do the occluding, that relative angle based on our distance, and we're just matching it up in Stellarium on the peak and seeing what matches.
Yeah, I guess it's where I'll have to figure that out because I don't understand how the tangent would be different from both locations, right?
Yes.
So then, but you're using the star height from the place that you're not at, from the mountain peak.
The mountain peak is part of my instruments, right? Like try to imagine instead of having like a little telescope, my telescope is 57 kilometers long, and it's resting on that mountain peak.
It's like you're overcompensating there a little bit.
Exactly. And then so then there's a star that's about to be in the center of my telescope, and when it's in the center, I'll no longer be able to see it, but only if my telescope is at that same exact angle, right at that 231 angle, and then what do you know? When it gets at that angle, we can no longer see it. And it's like, oh shoot,
Okay.
you were supposed to be at a lower angle.
I got it. And then where can I find those numbers? Because if I want to plug that in and play with it on GeoGebra.
Yep, I'm going to send you everything on Telegram right now.
Thank you.
Mm-hmm.
So if we're taking Stellarium to be accurate, can you tell me what your opinion is of the South Celestial Pole, Southern Circumpolar stars, other things that Stellarium says are real?
No, I would have to invoke things like a celestial sphere in the sky that projects everything out, or a celestial disk and stuff like that. So it's like it's more just a cosmological thing at that point, because the difference would be just ball curve, right? That's like the easy one. But if we're unable to find ball curve, anything's on the table really. But I personally haven't put much time into figuring it out in terms of like a lot of people are excited about trying to model it. I don't think it's something that we're going to be able to model it out with reflecting off of domes and things like that. I don't think that's
Yeah.
what we observe. I think we observe it all in our own azimuthal grid of vision, and what we see in the sky in particular, is unique to us. So
But everybody has the 69 miles per degree north or south.
yeah, that would just be a function of our optics. We all have like a radius of vision, right? That's our argument.
Okay. We have a radius of vision. So that's why it acts differently than, say, perspective, is because our vision is curved. And so the stars are at the outermost edge of our vision. Is that what you're saying?
No, are you talking? No, you're talking about being in the south and seeing them go around like a.
No. I'm just talking about, so like if you go north or south 69 miles, then the
Oh,
star moves by
yeah,
1 degree.
yeah. Sorry, I got you. Yes.
Right. Which is, 360 times 69 is 24,901 or
hmm
thereabouts.
hmm
Yeah. So I'm just wondering, how do we get that number then? If you're saying, because that's not how perspective works, right? Perspective would work by halves and doubles, or even, and it breaks down at the ends and the far end and the short end of the stick, right? Because things get larger much faster and get when they're close, and then larger much faster when they're, or a lot slower when they're far away.
Well, we
So
actually see in a logarithmic scale, right? Because we say curved visual space and we say hyperbolic because that's like the most familiar terminology that's in all the papers that describe curved visual space.
okay,
But if you plot it out, it's actually logarithmic. So what we have is like linear portions that go into a hyperbolic curve that then go into the logarithmic, like an L, like as it goes
okay,
exponentially. So when we plot that out, or when you look at, for example, the 69 miles per degree,
right,
that's in a linear portion of our vision. So if you were to take if you were to go like 20 degrees out to about 70ish, that portion on the graph is like the linear portions. That's where you're going to have the least amount of corrections needed. And when you look at the nautical almanac, that's where you have, that's where they recommend you take angles to the stars for everything, because that's where you're going to have the best viewing conditions for everything. And then when you get into stars that are further out at the horizon, further away from you, that's where they have the most extreme corrections. And that's where you get
right.
into the part of the scale where it becomes hyperbolic and then logarithmic, which is what we show. But, obviously you could argue that that's just due explicitly to refraction or refractive conditions. But we're saying that it's like the celestial navigation, the globes, all that is based off of this linear portion here. The most usable area of our vision is that's what's in reference to.
Okay, but we could just take Polaris though, right? And everybody work off that, and it would
Mhm.
move 1 degree per 69 miles.
Yeah.
And I guess I was confused why you're saying that would happen. If we're going off of our own personal atmospheric dome, that would be weird, because basically what's happening then is that we have a radius of circle that we are occupying of 24,901, because how else could you have 69 miles per degree and do it 360 times and get back to 24,901? Right. So when we were down in Punta Arenas, let's say, for example, I saw the South Celestial Pole, we work a certain amount of miles south, and then of course it wasn't dark anymore, so you couldn't see it. But I'm saying if you go that direction, then it's going to adjust 1 degree per 69 miles. So where does that break down on the Earth? I'm just wondering where it stops doing that. And if it doesn't, then what does that tell us? If because if perspective doesn't work that way, right? So for instance, if something's far away from us, we cannot move a certain distance, let's say 15 feet, and it adjusts 1 degree. And then we move
Mm.
another 15 feet and it adjusts 1 degree. And another 15 feet and it adjusts 1 degree. Nothing works that way in perspective. The only thing that works that way is the stars and
Yeah,
the sun.
exactly. So when we're
That's why I
talking
was
about,
asking if they
yeah,
were outside
right.
of our vision.
So in either model, they're
Mhm.
treated at the same distance away from you, which is 6210. They all use the same baseline, that same relationship for Polaris. Like that's what the whole latitude longitude system. Like when you talk about the globe, like you're referencing a star altitude capped at 6218 or 6210
Are you talking about kilometers? What is that number?
miles.
6210 miles is what?
The altitude of that's what they set the altitude of for all celestial bodies.
So Polaris, which is in my north, and another star that maybe is right above me, they're all at the exact same distance.
Yeah, that's how they treat them. They
Okay.
they they, they call it the celestial sphere. It's an equidistant web, and
Yeah,
that
it's funny. I've never heard 6210.
yeah. Well, that's what gives you the 1 mile per degree relationship.
That's what gives it to you?
That's the maximum distance you could be before Polaris would be,
Gotcha.
at 0 degrees on the horizon. Like you'd be at the equator, right?
Yes. Okay. I see what you're saying. So you're talking about because the distance would be 6,250 miles if you're at the equator to the North Pole.
Right.
Okay. I was just confused on that.
Yeah. No.
Okay.
So both models use that. Like that's what cell nav is based off of. When they talk about, because you know how they can do like parallax and to get light years and all that stuff,
Yeah.
right?
Right.
Like nobody does any of that. Like when they talk cell nav, when they're trying to figure out where to go, on the globe or using the latitude longitude system, right? They're using 6210 like as that for the altitude of the stars for that. That's what it comes out to be for the equidistant web. That's what creates that relationship.
From the surface of the Earth, everywhere that those stars are.
Mhm. Yeah, that's how they. So when they talk about what they would do back in the day, right? When they were putting together the nautical almanac, what they would do is they would cosine the stars essentially, right? And to do that, you have to have an altitude, and you have to have your angle, right? And then you could backwards derive what the distance would be. So that's what they were doing. But to set that altitude, they have to set it to something. So they set it to 60. Comes out to 6210, and then they would go and cosine stars, and then they would traverse the land, and then they would go. Then they would be about underneath that star, and then they would take zenith measurements of it. And then what they found was that the star was like almost. It was never in the center of their telescope like they would predict if everything was like. If their parallel rays were coming in and the Earth were flat and all that, like they expected it to be in the center based off of off of that relationship.
Okay. So you're saying if something is 6210 away from us, that there would be a linear change in angles, like 69 miles 1 degree, 69 miles 1 degree, just
Yeah,
because of the nature of being
for
in the mountain?
for that specific portion between about 20 and about 70, I think it is, whatever it says for the recommended.
Right.
That is the linear portion, yes, sir.
All righty. And are you saying that it would break down after that? So if you were at 80 degrees or 90 degrees, do you think then that it would move at a different speed? Or
You mean if you were you mean if you were at a different latitude?
Yeah.
No,
Let's
that's
say,
all. No, that relationship's always going to be the same. It's how far and you're perceiving, or like how far you're. I'm sorry, it's the angle that you're referencing for that you're doing it with, not your latitude. That's going to be the same.
okay, gotcha. So then the things in our personal atmospheric dome are going to appear at 6210 away from us in all directions, including underneath us.
Yeah. Well, when you're when you get to the horizon, right, you're not going to be able to see beneath you. So you could plot that as either, beneath your feet or, continuing on out of your field of vision, just using negative coordinates, it would be the same.
Perfectly half.
Yeah.
Seems a little strange.
Yeah. You see in a hemisphere standing on the ground.
Yeah, it just
When
seems
you
like
look up at the sky, you see about, what was it, like 4 quarter, or I forget the value, but it's like third
well,
of the sky or something.
you see half of the stars, right?
Essentially, yeah.
At all times. Okay, sounds good. Anything else for me?
That is it, sir.
Alrighty, that's fun. That's easy. All right, I'll look into it. I'll get back to you if you want to do it again, or if I have any things I come up with, because I got to think about that tangent line and how that works.
Yeah, let me know. And if you
All
need
right.
any other data or references or whatever, just
We'll do.
let me know.
Any questions for me before I go?
No, that's it, man. That's it.
Okay,
Take
good.
care.
You too. Take it easy. Later.
All right, lads and ladettes. That concludes episode 75 of Ether Roundtable. Tune in. What do we got coming up tomorrow? I think we have TikTok raids tomorrow. So we might be getting into some of that, unless literally anything else comes up. That sounds fun. So we'll do that instead. And then Friday will be a Twitter community space. And then Sunday will be Globebusters.